Today's lecture is about using randomness in a sort of limited sense to organize data. So recall last time's lecture about dictionaries and maps. These are data structures designed to let you insert, lookup, and delete key value pairs. They're extremely useful in practice. In Python, they're provided as a primitive, and we even form the backbone of the object model, same as JavaScript. In Java and C++, maps are ubiquitous interfaces, many possible implementations. The great thing about dictionaries is that they're really simple, and we'll try to argue today that they also have very good performance. Now, we already had two different strategies for implementing dictionaries. The first was to store everything in a big array, where the array is as large as the universe of all possible keys. Here we're assuming all the keys are integers, which is often the case because at some level, everything in a computer is represented by a bit string. The array allows for constant time access, but the problem is that the space is proportional to the size of the universe rather than the number of keys. The second strategy is search trees, like display trees from the third lecture of class. Display trees and other self-balancing search trees allow us to do insertion, lookup, and deletion in log n time. This is not as good as constant time, although not too shabby. But the good part of the search tree is that it really only needs a linear space with respect to the number of keys, because there's just one node for every key. Now, the arrays have constant access time in really bad space. The search trees have great space, but logarithmic access time. And the question we're interested in is, can we somehow get the best of both worlds? Can we get linear space and constant access? So we considered a very special case where we assume the integers are n keys out of the universe, but drawn uniformly at random. So we're not assuming, we're assuming that the keys are sort of spread out in sort of a completely random, unbiased way. And in that case, we analyze the following idea. Allocate a smaller array of size m, where m is some smaller number, probably proportional to n, and try to store each key in key mod m. Something like this. And in particular, if two keys happen to collide and they land in the same cell, append them together in some kind of linked list. Okay, so how well does this idea work? Well, it's clear upon inspection that every insertion, deletion, and lookup takes time proportional to the length of the list of the relevant array cell. And so that's what we really need to analyze, the length of each of these lists. So we asked, what is the expected length of a list? The length of a list is sometimes called the load. And what is the maximum length over all of the lists? This is sometimes called the max load. This kind of analysis is sometimes cast as a balls and bins type of problem. So here we think of us having n balls and m bins, and each ball gets independently thrown into a bin uniformly at random. And then we ask questions like, what is the expected number of balls in a particular bin? What is the maximum number of balls over all of the bins? So we analyzed these questions, and we showed the following. We showed that for any particular list, the expected load, the expected number of keys to go into an array slot, was n over m, where again, n is the number of keys and m is the number of slots. And we showed that the maximum load over all the lists was log m plus log n divided by log m minus log n, with probability at least 1 minus 1 over n. And we could have made the 1 over n smaller, and the bounds could have adjusted slightly. Okay. And to do this, we use relatively modest tools. However new, we use linear expectation, which we had used once before to analyze quicksort. And then we also introduced a new tool, but very simple tool called the union bound. In particular, we took the union bound over all the bins when analyzing the maximum load. And the homework asks you to improve the analysis and refine it in certain ways. Okay, but to go back to our question about dictionaries, we had arrays and we had search trees. Array had constant time, which was great. Search trees had O in space. That was also great. And the question was, could we get the best of both worlds? And it seems that in the special case where the keys are uniformly random, this strategy gets us closer and closer. In particular, if I take any epsilon greater than 0, then in roughly 1 over epsilon time, because that's basically the max load, I can do all my operations if my space is n to the 1 plus epsilon. So for example, we can set epsilon to be like 0.01, and then this looks like maybe the max load is like 100 or something, and the space is like n to the 1.01. So not quite n, but getting closer, and for each fixed epsilon, it still looks like constant time. Okay, so we found that for arrays, the best case is sort of n contiguous keys, the worst case is n keys spread out. And we found that n keys randomly spread out is actually pretty good. It's much further to the left of the spectrum, closer to the best case. But we still don't really have a data structure for the worst case when n keys are spread out, and they might be spread out, say, adversarially in a way that would make all of our lists completely pile up. So the question is, how can we somehow get the performance of n random keys for n adversarially selected keys? Okay. So what if the keys are not random? And here was the big idea. So the issue is we have these n integer keys, and they're sort of spread out over the universe, but we don't know how. And in particular, they may be adversarial lined up, like one every m slots or something, in a way that if we did something deterministic, it would generate a really long list and very high loads, very high max loads. So here we introduced the big idea. The big idea was to randomly reindex all of the keys first. So where you have some function h, which somehow takes keys from the first universe and sends it over to keys in a second universe. But the point of this function is somehow it should scramble the keys, and where the keys end up should look extremely random. And then we do the mod m strategy, where we take those keys and map it into a smaller space. Okay? So the idea was to randomly reassign new indices so that we can treat them as if they were random keys from a universe, and then use the simple mod m strategy. Okay? Now, this kind of function is called a hash function. So these are functions that take integers, possibly big integers, output other integers, possibly big integers. And in general, they should be relatively fast to evaluate, do some arithmetic of some kind. And they should act random. Like the output should really look random, so then we can get kind of a small load over all these bins. A couple of different hash codes used in practice are SHA-2 or the .hash code method in Java, for example. And the net effect, when we use a hash function to scramble the keys first, is that it'll look like we have a uniformly random mapping from the set of keys into the set of array slots. And as a result, all our balls and bins analysis from before should hold. But there was an important caveat to all of this. Really, no compact function can be truly random in the ideal sense we analyzed. And we'll go over this in just a moment, but the basic idea is that there's too many functions to express in so few bits. And we promised that next time, which is now this time, we would study some more concrete hash functions and figure out how to still make things work using a much more limited amount of randomness. Let's look a little more closely at this notion of an ideal hash function. Okay, so an ideal hash function, we have this function h mapping from some large universe to a smaller set of size m, where each HU is drawn uniformly at random, but in particular, each HU was drawn independently of one another. So what one U is drawn, one U's hash code was completely independent of the next U's hash code. Well, why independence? Why is independence so key? Well, in our analysis for max load, so here was our previous analysis. We said that the probability that a bin I containing at least k balls, so we focused on one bin at a time, was by the union bound, the probability that all balls in a set of size k goes to a bin summed over all possible sets of k balls, which in turn was n choose k, that's the number of ways to choose k balls, divided by m to the k, which is a probability that all k go to bin I. And independence is used in particular in this step here. We said that the probability that all k's go to bin I is 1 over m to the k, but for this we really need the fact that the balls, where they land, were independent of one another. Here now is another reason why we need to have independence. So here I'm going to give an example of a bad but still random looking hash function h that doesn't have independence across parts. So in step 1, I'm going to draw one index j out of the array, so maybe somewhere like here, uniformly at random. And then, for all the elements in the universe, I'm going to set hi to be j. So all of the keys are going to get mapped over to this one slot. And just pile it on there. Okay. Now, the good part of this is that if we actually look at any one item in any particular index j, the probability that hi gets mapped to j is still 1 over m, because j was drawn uniformly at random. But on the other hand, clearly all of the items are going to hash into this same bucket. We're going to get this huge list. So in particular, the max load is always equal to n. So all the keys will always go to the same bucket, even though we have this seemingly nice property that any index gets hashed to any particular slot uniformly at random. So that gives two different arguments why we should have independence, but now I'm going to suggest why we can't necessarily have full independence. And the argument I'm going to give sort of comes from information theory. So in general, and I'm going to be a little bit hand-wavy here, although you can make it more formal, if you need to identify k different objects out there and give them different bit streams or different IDs, you generally need IDs that are log k bits long. Really, it's a function of the entropy, but never mind that. The point is that to identify k different objects, you need about log k bits. And here, we take k to be the number of possible functions from our universe U down to the smaller set of numbers m. And so this is something like U to the, M to the U, because each element in the universe has m choices. And if we take the log of this, then we see that we need U times log m bits to sort of kind of write down, in general, any of these functions from an information theoretic point of view. This is a lot, even when the size of the universe is just n. Okay? So the point is that constructing ideal hash functions from a very kind of rigorous, although we didn't do all the rigor, from a rigorous information theoretic point of view is actually way too hard. So to recap, we know that having independence is good for load balancing. So if we store each key in its hash code mod m, and the hash code is completely independent of one another, then our balls and bins analysis from last lecture applies, and we know that the max load is going to be pretty small with very good probability. But the problem is that it's actually impossible to construct these hash functions, with pure and perfect independence in the sense that we analyzed last time. So the question becomes, are there weaker but still useful alternatives to total independence that A, we can construct, and B, is still useful enough to be able to implement good, somewhat randomized dictionaries? So now let's explore some of these weaker notions of independence and hash functions that have these properties. So we'll first start with no independence at all, just a uniform hash function. So this is where for each item I and each slot in the array L, there's equal probability of being in any slot. So 1 over m chance. And as we saw before, this is not good. So it's not very hard to come up with a hash function that satisfies this property, but really does not give us a load balance that we would want. Okay, the second notion is a little bit stronger. It's called a universal hash function. So this is going to be any hash function where for any pair of items I, j, which is I not equal to j, the probability of them colliding is 1 over m. Okay, so in fact, we're not even saying that the hash function has to be uniform or anything like that. All that matters to us is that the probability of a single pair colliding is 1 over m. This has nothing about, triplets of items or quartets or any combinations larger than just 2, but for 2 items, the odds of them colliding is 1 over m. Another notion is pairwise independence. It's similar to the above notion, so it's saying that for all I1, all items, pairs of items I1 and I2, and all pairs of slots L1 and L2, the probability that the first item gets hashed to L1 and the second item gets hashed to L2 simultaneously is equal to the probabilities kind of taken apart, the product of them. So in particular, it's equal to the probability that the first item gets hashed to the first slot times the probability that the second item gets hashed to the second slot. So this is what it means when we say things are pairwise independent. It doesn't say that anything about triplets or quartets, any combinations of more than 2 items. For any 2 items, though, their assignments are independent of one another. Now, if we take something that's a hash function that's pairwise independent and uniform, then we'll get that for any 2 items we're trying to hash, I1 and I2, and any 2 slots that we're focused on it going into, the probability that the first item goes to the first slot, given that the second item, you already know, has been mapped to the second slot. So conditional on the second item being mapped to the second slot, the probability of the first item being mapped to the first slot is 1 over m, still uniform. So with pairwise independence, even if you knew one of the assignments, all the remaining other items still have a 1 over m chance of being anywhere. Good. So why stop at pairwise independence? We can also define 3-wise independence. So here we have 3 items, I1, I2, and I3, and 3 slots, L1, L2, and L3. And it says that the probability of the first item going to the first slot, the second item going to the second slot, and the third item going to the third slot is going to be first the probability of the first item going to the first slot times the probability of the second item going to the second slot times the probability of the third item going to the third slot. Okay, so all the probabilities break up, and now for groups of 3, the hash codes are independent of each other. Why stop at 3? We can consider 4-wise independence. Now we have 4 items, I1, I2, I3, I4, and 4 slots, L1, L2, L3, and L4. And we ask, what is the probability the first item goes to the first slot, the second item goes to the second slot, the third item goes to the third slot, and the fourth item goes to the fourth slot? And 4-wise independence says all of these probabilities should break up independently. So we have a product, the first item getting mapped to the first slot, times the second item getting mapped to the second slot, times the third item getting mapped to the third slot, finally times the fourth item getting mapped to the fourth slot. So Now for groups of up to 4, we're saying that the probability of them, or the 4 items going into 4 particular slots, is equal to the probabilities as if they're all kind of independent and each choosing a different one uniformly. It doesn't say anything about groups of 5, only up to groups of 4. Okay. And in general, we can define k-wise independent for various k's. And, as sort of continuing the pattern from before, it's saying that the probability of this particular set of assignments to slots, so I1 to L1, I2 to L2, so forth, IK to LK, is equal to the probabilities taken alone, all multiplied together. The probability that I1 gets mapped to L1, I2, I3, I4, so forth, times the probability finally that the kth item goes into the k slot. Okay, so this isn't full independence. It's not like all combinations are totally independent of each other, but all combinations of size up to k are independent of one another. So we have now a number of notions of independence. They're a little bit weaker than full independence. We have universal hash functions, pairwise independence, 3-wise independence, and general k-wise independence. Okay, they're reasonable. But now we should ask ourselves 2 questions to try to get some use out of this. First, can any of these functions be constructed efficiently? Remember, the objection to totally random, perfectly ideal independent hash functions from before was that we can't actually store them any better than writing down the hash code for each key individually. So, but if we restrict ourselves and all we need is something like pairwise independence or universality or k-wise independence for relatively small k, then maybe we can come up with simple constructions that at least satisfy these properties. And second, if we did have a pairwise independent or k-wise independent function or something like that, is it even useful? Our analysis before totally used like having tons and tons of independence, but now if I have some limited notion of independence, can I still somehow get something useful out of that? So let's first consider the first of these 2 questions, whether we can construct one of these hash functions with a limited notions of independence, like universal independence, pairwise independence, k-wise independence, whether we can construct one of these functions efficiently. And we'll start with probably the simplest version of universal hash functions. This was the weakest notion of independence beyond not being independent at all. So how do we make a 2 universal hash function? Well, we start by choosing a large prime number p. So we choose a prime number p that's greater than u. And then we draw 2 random numbers. The first number, a coefficient a, is going to be drawn from the set 1 through p minus 1 uniformly at random. And then we're going to draw a second number b from 0 to p minus 1 uniformly at random. So we pick a prime number p that's bigger than the size of our universe, and then we draw 2 random numbers a and b. Now with that, we're going to define a hash function as follows. We define h of x to be equal to ax plus b first. So we take x and we compute ax plus b. Then we take this value and we compute its value modulo p. So here it comes that large prime number, so we compute ax plus b, and then we take it modulo p. And then we take that whole thing, and after modulo p, we take the value mod m to ultimately output a number between 1 and m. Okay, so that's the idea. So schematically, it looks something like this. So in the first step, we're going to take all the keys and we're going to compute their values ax plus b mod p, and we're going to hash it to actually a larger universe. So the second array is going to be of size p, and this is actually bigger. And then we're going to take these larger values modulo p and hash them down to something just by taking mod m. Okay, so that's the overall construction. We get these large values ax plus b mod p, and we take it down to m. And keep in mind that this hash function we're defining is in many ways very simple. We're just doing ax plus b. Okay, so that's the construction. Ax plus b mod p mod m, where a and b are chosen uniformly at random. And now our big claim is that this hash function is universal. And just to remind you, a universal hash function is one where the probability of any 2 items colliding is just 1 over m. Okay, so to prove this claim, we're going to need some lemmas. So the first lemma, in the first lemma, we fix x1 and x2 to be 2 different items that we're hashing. And then we're going to look at these choices of a and b, and we claim that a and b are in 1-to-1 correspondence with their possible outputs. These are values ax1 plus b and ax2 plus b that are not equal. Okay. So let me try to rephrase this lemma in maybe a way that's a little more direct to prove. Let x1 and x2 be fixed and not equal. And then let's fix 2 possible kind of output slots, C1 and C2, again, not equal, mod p. We claim that this system of equations on the left, ax1 plus b is equal to C1, and ax2 plus b equals C2, So here, x1 and x2, c1 and c2 are fixed, and the variables are a and b. And we claim that this system of linear equations uniquely determines a and b. So if you knew the values of c1, c2, x1, and x2, and you knew this system of equations held true, then you automatically know the values of a and b. Okay, so let's prove this, which is just a matter of algebra. So to prove this lemma, we first write down our system of linear equations. ax1 plus b is equal to c1, ax2 plus b is equal to c2. We take one and subtract it from the other. Okay? So we do ax1 plus b equals c1 minus ax2 plus b equals c2, and we get something like a x1 minus x2. And here the b's cancel out, and that's equal to c1 minus c2. Okay? And now it's important that x1 is not equal to x2, and their difference is not 0, so that we can do division. So a is equal to c1 minus c2 divided by x1 minus x2. In turn, we get, so that determines a, and in turn for b, we have b is equal to c1 minus a times x1. So now we can plug in the value of a we just obtained times x1. And now we found a and b as a function of c1, c2, x1, and x2. So an important note, why are we even allowed to do division at all? Up here, it's because p is prime. And when p is prime, the set of integers modulo p forms a field where division is well defined. So in particular, a divided by b is defined as a unique value of c such that bc equals a, and sort of a elementary abstract algebra shows that this is well defined, c always exists, and c is unique. Okay, so we've proven that lemma, that knowing c1 and c2 determines a and b. And now let's prove a lemma that looks a little bit more like something related to hashing. Okay, so lemma is fix x1 not equal to x2. Then we claim for any fixed choice of two output slots, c1 and c2 not equal, the probability that both ax1 is equal to c1 and ax2 is equal to c2 is 1 over p times p minus 1. So to be clear, x1, x2, c1, and c2 are fixed. The randomness is over a and b. Okay, so that's the probabilistic statement. The randomness is over a and b, and we claim that the probability of these particular items going to these slots mod p is 1 over roughly the prime number squared. Okay, so for the proof, we just used that previous lemma from before. We know from our previous lemma that for any choice of a for c1 and c2, there's exactly one choice of a and b. And the number of possible choices for a and b was p minus 1 for a, and b was in the range 0 to p minus 1. So we have p choices for b, and that gives us 1 over p times p minus 1 probability. Okay, good. So we have that lemma, and now we can try to prove the big theorem that we're interested in all along. Let h of x be this hash function we've constructed. So we're doing ax plus b modulo large p, where a and b are chosen randomly. And then we're taking that value mod m. And we claim that this function, which is going from the universe down to just m slots, is universal. Or again, we remind ourselves that universal means that the probability of two items colliding is 1 over m. Okay, so let's prove the thing. And we want to analyze the probability that for a particular x1 and x2, the probability that their hash codes, which is modulo m, are equal. Okay. And to analyze this, we're going to parameterize by their possible values at the mod p stage before taking mod m. So first, we're going to say, okay, let's say that ax1 plus b is equal to c1. So here c1 is going to range over all the values in this field. And then we're also going to say, okay, and then we'll say that ax2 plus b is equal to some value c2, where c2 is equal to 1, from 1 up to p. But here, we know that the collisions can only occur for very specific choices of c2. In particular, we have that c2 is not equal to c1, but also c2 is equal to c1 mod m. So good. Now, we know from the lemma up above here that the probability that ax1 plus b is equal to c1 and ax2 plus b is equal to c2, that this is equal to 1 over p times p minus 1. So we drop that in. Okay. And then we're still summing over c1 from 1 to p. And now we need to count the number of possible c2s for this possible value of c1. So this is a number of choices of c2 in the range 1 to p, such that c2 is not equal to c1, and also c2 is equal to c1 mod m. Okay. So how many of these values are there? Well, here maybe I've written out all the numbers from 1 through p, and say C1 is here in red on the left, and then we walk a fixed number of steps m, and we get the first possible value of C2, so maybe C1 plus m. Another m slots over, you get C1 plus 2m, and so forth, up to some C1 plus km, where k, one can show, has to be at most p minus 1 divided by m. Okay. So good. So that limits the number of C2s, and plugging all that in, we get 1 over p times p minus 1, that's from above, times p from the summation, times p minus 1 over m, which is the number of choices of C2. Okay, so what did we show? We showed that these particular items, two items, x1 and x2, the probability of them colliding was 1 over m, and there was nothing special about x1 and x2. This applies for all possible choices of x1 and x2, and this is the definition of a universal hash function. So indeed, we can make one of these things. So we've now been able to give a construction, a fairly simple construction of a two universal hash function. We pick a large prime, and then we do ax plus b mod p, and then mod m, where m is the kind of the output array. And we're able to show in particular that this construction, however simple, is also universal. So that's great. We can actually construct universal hash functions. Moreover, it's pretty easy. We just choose two random numbers. But there's still that second question. Is having a universal hash function, so we don't have independence in any complete sense, but we know that the collision between two items is relatively small, as if it were independent. Are these functions even useful? Can we make a dictionary out of a simple ax plus b? So here then is the full schematic. We start with this large universe of size u, and then we map ax plus b mod p into this even larger universe of size p. And then we take everything down to the smaller array of size m. Okay? And now we know that when we do an operation, like I want to insert one of these keys, then the running time is really going to depend on the length of the list wherever the key gets hashed in. So the expected time for looking up some key k is equal to the expected value of the load at whatever slot it gets hashed into. And in turn, the expected number load of the slot that it gets hashed into is going to be is 1 plus the expected number of other keys, j, that have the same hash key. So hj is equal to hk. Okay. This 1 plus here is for k itself. So the load of itself will include itself, and then it will be how many other keys collide with it. Okay, so we can analyze this thing. The expected number of other keys j, which hj equals to hk. And here we invoke the very powerful linearity of expectation again. And we can break it into a sum of all the other keys. The probability that this other key j has the same hash code as k. And here we can take advantage of the fact that h is universal, which in turn implies that this probability is 1 over m. Thus, when we put everything together, we have n minus 1 other keys, and each of these keys will collide with this particular key k with probability 1 over m. And now we have an algorithmic theorem. In particular, we've shown that with a two universal hash function, or just universal hash function, the expected time for every operation is big O n over m, because that's the expected load of, or an expected number of collisions for any particular key. Okay, so that's good. So we've now shown that expected time per operation is big O n over m. That said, when it comes to things like analyzing the max load that we did last time, in fact, universal hashing does not imply anything about having a small max load. Why? Well, I'll leave it to you to go back to the analysis of max load and figure out where exactly we needed full independence. So what can we say instead? Okay. Well, we showed that the expected number of other keys j that collide with a key k is n minus 1 over m. Now we can now claim the following. I want to know to what extent things will deviate around this n minus 1 over m average. I claim that the probability of the number of other keys j colliding with k being more than, say, 10 times the average, 10 times n minus 1 over m, is at most 1/10. Similarly, I'm going to claim that the probability that the number of collisions with k is more than 100 times the expectation is at most 1 over 100. And even more boldly, I will claim that the probability that the number of collisions with key k is greater than 1,000 times the expectation is probably at most 1 over 1,000. Okay? And in fact, the proof is quite short, but we're going to use another very powerful, but also fairly simple probabilistic tool called Markov's inequality. So what is Markov's inequality? Markov's inequality starts with a non-negative random variable x, and also involves some coefficient alpha greater than 1, like alpha equals to 2. And it's about how often x deviates from its average. In particular, the probability that x is greater than or equal to alpha times its expected value is at most 1 over alpha. So for example, if we set alpha equal to 2, it's saying that the probability that x is greater than or equal to 2 times its average is at most 1 over 2. The probability that a variable is 2 times its average is at most 1/2. Okay, why? Well, if we think through this just carefully, I think common sense will actually prevail. So, if x is greater than or equal to 2 times its expected value, more than half the time, so this is a proof by contradiction. Suppose that the random variable x is more than 2 times its expectation more than half of the time. Well, then we know that the expected value of x is at least, first, the probability that x is greater than or equal to 2 times its average times, well, if it's greater than or equal to 2 times its average, then it's going to get 2 times its average many points. And here we're dropping any value that comes from when x is smaller than 2 times its average. X is still non-negative. This is where non-negativity comes in. Okay. In turn, this is greater than, we're assuming that this thing is greater than 1/2, and then that 1/2 at a time you get this many points, but this is equal to the expected value of x. So some level we've shown that the expected value of x is greater than the expected value of x, and this thing is a contradiction. Okay? So similarly, if x is greater than or equal to alpha expected value x, so now alpha is just some variable, it could be 10, it could be 100, it could be 1,000. If x is greater than or equal to alpha times the expected value of x, more than 1 over a fraction of a time, then so on and so forth, I think it's clear what the pattern is. I'm going to let you guys try it out for yourself. So, okay, that's where we get all these inequalities from. The probability that the number of expected collisions with k being 10 times the expected number of collisions is at most 1 over 10. The probability that the number of collisions is more than 100 times its expected number of collisions is about 1 over 100, and the probability that the number of collisions is at least 1,000 times its expectation is at most 1 over 1,000. So here all these just are immediate applications of Markov's inequality, where we set x to be the number of other keys, the number of collisions, the number of other keys that have the same hash code as k, which we need to point out is always non-negative.